Simply a powerful classification algorithm that you can easily implement. This is naive Bayes theory, practice, and its mixed variant. This is historical data of 14 game days showing whether the game was played or not. What do you think about the status of upcoming day 15? We can simply estimate the probability of play 9 play days divided by total 14 game days and likewise no play. This would be our initial guess or belief about upcoming game days, 64% chance that the game will be played and 36% that it will not. Since probabilities must add up to 1 and there are only 2 outcomes, either play or no play, we can actually estimate one of them knowing the other using the complement rule. The first rule we are going to learn about probabilities. So if we know the probability of play, then the probability of no play is simply 1 minus probability play. No play is also called play prime, which is simply the probability of play not occurring. These probabilities are known as priors, which is an estimate of game day status knowing nothing about the day's feature. Our friend here will save these priors for us as we are gonna need them later. Now let's add some features. We'll focus on the weather data for each game day. These are categorical features that consist of several categories or levels. We can summarize them using contingency table or crosstabs, displaying frequencies for a combination of 2 features. For example, overcast and cool, there is only one game day where outlook was overcast and temperature was cool. Rain and cool 2 days, rain and hot no days, and so on. Let's say that we are interested in finding the probability of rain or hot. We can simply add them together, which is equivalent to 64%. And this is the sum rule. We were able to add them directly together because they are mutually exclusive events. If we look at the data itself, we can see that they never occur together. Rainy days are not hot and vice versa. Such relationship can be visually displayed using Venn diagram. A Venn diagram is a simple way to visualize event and relationship between them using rectangles and circles. The rectangle represents the sample space, 14 days, and each circle is the portion of days where the event of interest occurs. In our example, rain and hot, circles are separated. There is no overlap because these events do not occur at the same time, thus disjoint, which is another word for mutually exclusive. What if the 2 events were joint, which means that they can happen at the same time? Then we simply account for this when adding them together by subtracting the common occurrence. For example, if we look at our data, we can see that events sunny and hot can happen at the same time. The first 2 days are sunny and hot. Thus, P sunny or hot will be P sunny plus P hot minus P sunny and hot, equivalent to 50%. Which actually makes sense because if we look at the crosstab, event hot has 4 occurrences where 2 of them are associated with being sunny. Thus, 50% probability of sunny or hot. These events are non-mutually exclusive, can occur at the same time. When we look at the Venn diagram, we can see 2 days at the intersection of these events, which if not subtracted would be double counted. 5 plus 2 plus 4 would be greater than the total event days. Or here means either or both of them occurring, not just one of them, so it's either sunny, hot, or both sunny and hot at the same time. Thus, the sum of their probabilities is larger than their individual ones. Let's explore the multiplication rule utilizing only crosstab to save up some space. We'll add another layer of distinction between events being dependency. When 2 events are dependent, it means that they do affect each other, so knowing that one event has occurred tell you something about the other. Dependent event can be disjoint. For example, we know that rain and hot are disjoint events, thus the probability of rain and hot both occurring at the same time is simply 0. We can see from the Venn diagram that there is no overlap between these 2 events as they can't happen together. Now, you might ask yourself, if they can happen together, how come they are dependent? They must be independent, right? This is why we need to distinguish between the 2 definitions. If I tell you that rain has already occurred and you know that they can't occur at the same time, this means that P hot must be 0 at that time, thus knowing that it rained told you something about being hot. And this is the definition of dependency. You can think of joint states as the timing of occurrence, while dependency as the change that one event brings to the other. In general, we can conclude that disjoint events are always dependent. On the contrary, joint events do have some overlap and we can expect their intersection is not equal 0. For example, P sunny and hot is equal to P sunny multiplied P hot given sunny, which is the probability of hot when sunny has already occurred. This is equal to 14%. If you look at the Venn diagram, we can see the 2 days when it was sunny and hot at the intersection of both events. But what if the joint events were independent? Knowing that sunny has occurred does not affect the probability of hot. If that's the case, we simply multiply the probability of both events together. We can immediately notice a difference between both calculations. Which one is correct? Well, we need to make an assumption about the state of dependency between these 2 events. One way to derive such assumption is to test for dependency. For example, if P hot is equal to P hot given sunny, this means that they are independent because in that case, sunny has no effect on being hot. They are also independent if p sunny and hot equal to p sunny multiplied p hot. That would be 2 divided by 14 equal 5 divided by 14 multiplied by 4 divided by 14. Since this event did not pass the test of independence, we conclude that they are dependent. So 14 is the correct one. These were just some of the tests we can do, but it will actually be overwhelming to do such tests each time we want to find the probability of intersection of two events. Instead, we can directly use this rule that is known as general multiplication rule. It is general because if these events were truly independent, then p hot would be equal to p hot given sunny, thus will give the same result, as sunny would have no effect on being hot. This expression, p hot given sunny, is the conditional probability of two events, that is the probability of one event knowing that the other has occurred, the probability of hot knowing sunny has already occurred. I like to remember it using the get into rule. Just for memorization purposes, you simply get into what is after the given sign, in our example sunny, and find the probability of what's before the given sign, in our example hot. Since our event or feature are categorical, this means filtering all sunny events and taking it to the denominator 5, then using count of hot events as numerator 2. Get into rule is your friend, as you will see later. Lastly but not least, just remember that and means the intersection of two events. This is a specific event, thus smaller than their individual ones. When it comes to supervised machine learning classification problem, we are actually interested in predicting the target variable. That would be the play status of each game day. Let's focus on single feature of game day and summarize this data using contingency table, where rows represent feature frequency and column represent target ones. Using Bayes' rule for predicting the status of game day based on the day's outlook would tell us that probability of class given evidence, that is the probability of yes given sunny, is equal to probability of yes and sunny divided by probability of sunny. When we expand this utilizing the knowledge we have so far, p yes and sunny is equal to p yes multiplied by p sunny given yes divided by the same plus p no multiplied by p sunny given no. A lot of this stuff looks familiar, right? First of all, p yes and p no are the class priors we calculated at the very beginning, and we said that they are our belief or expectation of game day status, knowing nothing about the day's feature. What we are trying to do is to update our prior belief giving the new information we have, which is the day being sunny. This is known as posterior probability, and it is basically the conditional probability we have discussed earlier. Probability of play knowing that it is sunny. The numerator is the general multiplication rule, and the denominator is the probability of sunny based on play status. If we substitute the number, we get the probability of 40%, which is equivalent to 2 divided by 5, the get into rule. So what Bayes' rule simply does is utilizing general multiplication rule to update the priors by finding posterior conditional probability of class given evidence. For this categorical feature, it is basically the frequency of class 2 play days given evidence 5 sunny days. If we do the same for class no, we get 60%. When compared to prior, our initial guess of game status would have been 64% probability that the game will be played and 36% probability that it will not. However, incorporating additional piece of information, which is weather condition sunny, we update our initial guess towards higher no play probability, which makes sense as sunny is mostly associated with no play days. We can actually derive probability no given sunny either by complement rule or the made up get into rule. This can get a bit complicated. For example, according to our data, overcast and no play do not happen together. It's problematic because when applying the general multiplication rule, we'll get 0, specifically for class no. This is known as the zero frequency problem. Why should we bother? Because it doesn't make sense to estimate the probability of some event to be 0 just because it is not present in our finite data. Maybe in another sample of game days, these two events happen together. In addition, our data consists of many features, and as we will see later, when it comes to classification, we multiply several conditional probabilities together. If one of them happen to be 0, it will mess up the whole calculation, leaving us with 0 probability of such class. To overcome this, we use smoothing technique by simply adding 1 to all the counts. Note that in the numerator we added 1, but in the denominator we added 3 because our feature has 3 levels or categories: overcast, rain, and sunny. Think of it as adding 1 positive sample to each category per class. We have also ignored smoothing the prior, since we will typically have a fair fraction for each class and a reasonable estimate of associated probability that will be quite far from 0 anyways. This will give us smooth posteriors, and if we compare it to priors, we can know that it actually makes sense as it's more inclined to yes class, where it is usually a play day when it is overcast. This is the smoothing formula, x plus alpha, where alpha is the smoothing parameter. In our example, 1 divided by n, the total number of samples per class, plus alpha multiplied k, where k represents the categories or levels per feature. This is known as Laplace smoothing or additive smoothing. Adding more features to the mix, we can extend Bayes' rule to accommodate multiple features, so we will add humidity to the feature space and summarize data in the form of contingency table. If we are interested in the probability of yes given sunny and high, it would be complex to compute the probability of evidence given class for each feature and each class. Imagine doing this for 100 features, not just 2 features. So instead, we are gonna make a naive assumption of class conditional independence. Once we are in the class realm, we will assume that features are independent of each other, allowing us to utilize the multiplication rule for independent event, which makes the calculation much more easier. This is the origin of naive word in the naive Bayes classifier. It's actually a strong assumption, which means that for each class, play or no play, there is no correlation between each feature. That's why we need to watch for highly correlated features and assess their impact on our model. Now just substitute the numbers and derive the probabilities. So we learned that Bayes' rule consists of 2 parts, the numerator, which is PC and evidence, and the denominator, which is the probability of evidence. Let's just focus on the numerator and assume that we wanna predict day status when it's sunny and high. In that case, P class and evidence would be 5% for class yes, which is the likelihood Px given C, multiplied by P class. By the way, these probabilities are the parameters of naive Bayes classifier. Note that I'm switching between notations. Sometimes I refer to feature as evidence, another as X, so that you are familiar with the different notation used out there. Some people use A and B as reference, others use E for evidence and H for hypothesis instead of class. If we do the same for no, that would be 17%, so we can actually derive our classification decision at this point based on these percentages and assign this game day to no class. In other words, our decision rule is argmax PC1 given evidence, PC2 given evidence. Argmax or argument of the maxima are the input arguments or values at which the function output are as large as possible. This is known as maximum a posteriori estimate. It simply answers the question of which class these features, sunny and high, has a high likelihood of belonging to. So we are basically saying that these features are highly likely to belong to no class based on our prior knowledge of class distribution and the conditional probability of these events given each class. Since we have 2 datasets, features or X's, one for yes and another for no class, the data that maximizes the conditional probability of class is the maximum a posteriori estimate. Just similar to the concept of maximum likelihood estimate, but incorporating the priors. If you are not familiar with maximum likelihood estimate, I have another video linked above and in the description box where I explain probability distribution function and their related concepts. These figures are unnormalized probabilities and they do not add up to 1. We can simply normalize them dividing by the denominator of Bayes' rule, which is the probability of evidence. So yes, we get 22% normalized posterior probability, and for no, we get 78%. As you can see, even after normalization, we are still classifying this game as belong to no class. Thus, to maximize PC given evidence, it is sufficient to maximize PC and evidence, completely ignoring the denominator since it is positive and constant for each class. So far, we have been using limited number of features. What if our dataset contains several other features that are not categorical? Our objective is to maximize PC and X, which is equivalent to maximizing PC given X. The first step is to make an assumption about the distribution of each feature in our dataset. We know that outlook is a categorical feature, so P outlook given class follows a categorical distribution with parameter n divided by m, where n is the count for each level category and m is the count of total samples or observation per class. This is also applicable for discrete representation of categorical feature known as multi-nollie distribution, where the representation of sunny, overcast, and rain would be changed to 1, 2, and 3. Humidity is the same as outlook. Wind is discrete variable of only 2 outcomes, 0 and 1, yes or no. So P wind given class follows a Bernoulli distribution with parameter P, where P is the probability of success, and success here is the occurrence of the feature represented as ones. So it is the average of ones. Pressure, air pressure, is a continuous variable that is normally distributed, so probability pressure given C follows a Gaussian distribution with parameters mu and sigma, where mu is the average and sigma is the standard deviation. Add days is a discrete variable that represents the number of days where the game was successfully advertised in the month preceding the game day, so it's 1 if the ad was aired and 0 otherwise. So probability of add days given C follows a binomial distribution with parameter n equals 30, where 30 represents the number of days per month. Finally, tickets sold is a continuous variable that represents the average price of tickets sold for each game day, so P tickets sold follows a uniform distribution with parameter A and B, where A is the minimum value and B is the maximum value. Simple approach to know the distribution of each variable is to look at the histogram. I highly recommend checking my linked video here and in the description box, where I discuss probability distribution function, because these are the core concept of what's coming next. We will consider that this is our training data from which the model will learn the underlying pattern. The next step is to estimate the parameter of each distribution for each class. So let's focus on pressure feature. We will split the data into two, one for each class, then simply calculate the mean and standard deviation for each, which represent the maximum likelihood estimate for the parameter of the distribution at this point. Next, we will store these estimates in our parameter box for later use. We will also do the same for add days, then update our parameter box. We now are ready for classification. If you are wondering how did we estimate these parameters, for pressure feature it is pretty straightforward. Finding the mean, which is the average of all the values, and standard deviation, which is the square root of variance. If you are not familiar with these calculations, check my linked data analytics video. For add days feature, we already know that n equals 30, representing the number of days per month. In that case, P would be the probability of success, area of add, calculated as an average of all observations. So for example, for game day 1, P equals 7 divided by 30. For game day 2, P equals 8 divided by 30. And overall P is just the average of these averages. For simplicity, let's assume that our data consists of only these two features, pressure and add days, and let's retrieve distribution parameter from our parameter box. Our unseen or new game days that we wish to predict the play status have these values for each of these features. We are using the same training data to make prediction, but let's just pretend that this is a fresh data that we haven't seen before. So our objective is to maximize probability of C given E, which is equivalent to maximizing P, C, and E. Since our data is mixed, then we derive the conditional probability of pressure given yes using the probability density function and our estimated parameter mu and sigma for class yes, and the conditional probability of add days given yes using the probability mass function and our estimate parameter of n and p. What is probability density function and probability mass function? That answer you will get from linked video above and in the description box. And just do the same for no class. That's pretty much it. If you expand our example to include all the features we have just discussed, it will follow the same concept, deriving px given c following the assumed distribution, then maximizing pc and x. For discrete Bernoulli distribution, the probability of non-occurrence is accounted for when computing pc given x. For example, feature wind, we will account for the non-occurrence of zeros when calculating pc and e. So if it is 1, then p is simply the probability of success, and when it is 0, it is the complement. This is because only Bernoulli model models the absence of feature explicitly. Before we move on to the implementation, let's summarize what we have learned so far. We first make an assumption about the distribution of feature, estimate the prior and the distribution parameter, calculate the conditional probability px given c, hashtag get into rule, finally maximize pc given x, which is equivalent to maximizing pc and x. Hopefully you are now excited and ready to see all this in action. Let's code mixed naive Bayes from scratch and also learn about machine learning workflow.